Welcome, y'all, back to some more Algebra 3. We're looking at our last part of R.7 before our test. All right, so we're talking about rational exponents. So we know what exponents are. These low numbers usually above our base number here. So if we're square rooting this, we understood out here, this is understood what out here? So understood 2. When there's no numbers, understood to be a 2. And then at the same time, we look like, what's the exponent on this number right now? What number is right there? It's a 1. Yeah, it's understood 1. These numbers are there all the time, but because of their relation to the whole system, they're understood. That's the word, understood. If this number is not, if there's nothing here, understood to be a 2. If there's a number here, no number here, it's understood to be a 1 on that. So 4 to the 1 power is 4. The square root of a number, the square root as in like 2 numbers. So this right here and this right here are the exact same thing. I'm asking you, what's the square root of 4 in fraction form? So that's what these rational exponents are. They're just converting something like this to this. And we'll see, like, well, why would we do that? We'll see here in a bit. So here, say, hey, what's the square root of 4? It's 2. You understood that. Here, say, what's the square root of 4? And look at the number like this. You'll say, I can't take half of that. But let's convert the 4 into powers of 2. So 4 is made up of 2 times 2, or 2 square. So that's 2 square to the 1/2 power. These two exponents that we talked about back in, I think, R2 or R3, when we have a power to a power, the same thing as saying 2 squared times 1/2. The exponents are multiplying. Well, 2 over 2, when we do that, we get 2 to the 2 over 2 power, which just gives us 2 to the 1, or just 2. Now, this is a long version because I want you to see exactly what happened. But yeah, here from the very beginning, say, oh, those cross out. So I just got 1. But I wanted to show you exactly what happened mathematically. So this seems a little bit more complicated in this sense. Kind of. Let's see. So let's kind of look at how these work. So if you have some power to the 1 over n power, that denominator here is the root we're looking for. How many root numbers? The radical index numbers is called. Yeah, the index number. Since this is the 1's technically right here, but remember, it's understood, so we don't put it now. If there is a number greater than 1, such as x to the y over n, then the y, well, again, can either be written like this, or it can be written like this. And x to the y can be under the radical. They both have the same meaning. Whether it's outside the radical or inside the radical, it's typically the same. Now, to refresh again, that's a fraction. If you have a negative exponent, even if it is a fraction, this whole thing will move down to the denominator. And since there's nothing above, you put an understood 1. And then from here, you can work it out. 1 over the n root of x to the y power. Sometimes that's easier, sometimes not. So we're going to practice both of them. So we're going to practice converting these to radical notation. So with a radical. And so this particular problem, this is our exponent still. This is still the exponent on the base number. And this is the index number, index for the radical. So when we rewrite this, this would be radical to the 4th power of 7 to the 3rd. Now you can leave like this because 1, can 4 go into 3? No. And from the very beginning, can 3 be divided by 4 evenly? No. And we can't simplify the 7 anymore. So we're good right here. We are done. But let's look at this next one. We got 8 to the negative 5 over 3 power. That's a good one right here. So first off, let's get rid of this negative. Let's take care of the negative. The negative's too much. So then this becomes 1 over 8 to the 5 over 3 power. There we go. Now, let's try to simplify this. So let's write it as a radical. So you get 1 over the 3rd root of 8 to the 5th power. Oh, look at that. All right. So let's try to simplify. And actually, I'm going to write the 5 on the outside. And you'll see why. We'll see why. What am I looking for? Oh, the back button. There you go. I'm going to write the 5 out here. I'm kind of treat it like that first one we did, where this is in parentheses like that. So we're looking for the 3rd root of 8 only. We'll leave it like that. And the reason that's a little bit more simple because 8 does have a 3rd root. 8 can be broken down to 4 times 2, which is then 2 times 2, or 2 to the third power. We can rewrite it as the cube root of 2 to the third power to the fifth, like that. Now, can that 3 go into that 3 evenly? It sure can. And when that happens, you just get a whole number 2. But it still has that 5 on the outside. So now we have 2 to the fifth power, also known as 1 over 32. 1 over 32. So this is why sometimes it's easier to have that power on the inside or have it on the outside, like we had it earlier. Because you could take it 3 into the 5, no problem, and have your remainder 2, but then you still do one more step. But by doing this, where we take that out and only work with this, we're able to simplify a little bit easier. So look at this particular problem right here. We're saying m to the 1 over 6. Remember, this is the index number. So you still have your m. That's your base number. You have your radical, your index number, 6, and it's an understood 1. Can we do anything past this? No. So just leave it like that. You'll be fine. All right. And this next problem right here. Now, this negative right there, that is strictly on the 32, not the exponent. So we won't do what we did here. So let's convert the same thing like last time. We're doing this, has a power 2. We're doing the fifth root. So radical 5, and it's negative 32. And just like the last one, I'm going to put the 2 on the outside because we can simplify this a little bit more. So 32 is what? 16 times 2. 32 is 4 times 4, which each of these have a 2 each. 2, 2. So I have 1, 2, 3, 4, 5, 2. So I can rewrite this as the fifth root of negative 2. And it's negative 2 because to the fifth power. The reason we have to be very explicit is negative 2 times negative 2 times negative 2 times negative 2. That's all positive 16. But then times the negative 2 makes it negative 32. So there's a negative throughout this whole thing. And really, you can even keep it right there from the very beginning. I'm going to separate just 1. All right. So this is what we have. And this is to the square. But we can simplify this. Can that 5 go into that 5 evenly? Yes. How many times? Just 1. So 1, negative 2 comes out. And then you have the square on the outside right here. You square that. Negative 2 times negative 2 is positive 4. There you go. So we're converting. So part of your homework, you convert just a radical and simplify as you can. The other part of your homework is you can convert these to exponential notation, kind of like what they were before, and then see if we can simplify anything there. So here, just like the bases right there, again, this is our index number. Our index number will also become our denominator. And then this will be our numerator. So we rewrite this, so we still have the base the same, 7xy. And then the power is 5 over 4. Like that. Now we're just converting. We're not simplifying in this case. Now when it says, we'll do a problem here where it says simplify, this is a different story. You can reduce as you do right here. Look at this problem. We have the 3 on the inside. It's no different than if the 3 was on the outside. So when we write this, this is our numerator. This is denominator. It's x to the 3 over 6. Now, can that reduce? Yeah. It's x to the 1/2. And that's it. We're good. So that's one step that has to happen. Just reduce it if possible. All right. But let's look at our last little bit right here. You're going to simplify these. And if appropriate, we're going to write this in radical notation. And we'll see why. This is a perfect example right here. Now, these two are multiplying. The bases are multiplying. When the bases are multiplying, these add up. Our exponents add up. Can we add 5, 6, and 2/3 as they are? No. We need a common denominator. In this case, it would be 6. So we're going to leave this first one as it is. X 5 to the 6. But to make a 3 into a 6, I multiply that by 2. So I got to do that to the top as well. So we get x to the 5 6 times x to the 4 6. Now, because the denominator is the same, I mean the base is the same, and now the denominator is up here the same, we can add this. So we get a single x, and then 5 plus 4 is 9. We get 9 over 6. Now, can this reduce? Yeah, they both reduce by 3. So you get x to the 3 over 2. Now, here's the thing. This can simplify. Now, the reason we want this in radical form, you see why. Now, how many times can 2 go into 3 evenly? 1 time. So we get 1x out, and then we get a remainder of 1. Now, it comes out like this because it's 2 over 2, which becomes 1, which if it's just a 1, we don't write anything. So that's why we leave it as x times x to the 1/2. Here's the thing. This is very ugly, per se. And not to be like, spirit like, but this looks improper. You're technically not wrong, but it's improper. It's better than, because this is a 1/2, let's switch that to radical. This is why it says when appropriate, this is an appropriate reason. We have two different bases right here. So let's just do our x and then radical x. This looks a lot more clean and a lot more proper. So we're going to leave it like that. And this is the right answer. Again, this is not a wrong answer. It's just not aesthetically pleasing as much as this is right here. All right, so this is the problem. One of the biggest issues when it has something like this, when it's off from what we normally are, we want to then like try to distribute this. And one, we've never done that. We don't distribute into something's adding. Now, if they're multiplying, x times 3, then that's a different story. You can do that. But since they're adding, that's not how it works. But we have the same base here. So then they just focus on these. Do they have the same denominator? Yeah. So what's 5/2 minus 1/2? That's x plus 3 to the 4/2. And can 2 go into 4 evenly? Yeah, 2 times. So this becomes x plus 3 squared. And leave it like that. You do not have to simplify. If we're just simplifying, you don't have to then factor it out, take x plus 3 times x plus 3. No, you're good right here. All right, one more time. So let's look at this problem. So we got the cube root of the square root of 7. So let's focus just on this part right now. So if we're turning that into a exponential problem, we have our cube root, and this becomes 7 to the 1/2. Yeah, 1/2. Now we're going to turn this, so we're good right here. So this is our base. Put this in parentheses, 7 to the 1/2. Now, since we're going to then convert this, again, what is technically the exponent on just this whole thing? It's understood 1. So when we convert this to another exponent right here, the whole thing, that's 1/3. So we got 7 to the 1/2 to the 1/3. And similar to this, when you have a power to a power, like here we added them because it's base times base, but here we have a power to a power. We multiply these numbers. So we could take 1/2 times 1/3. We don't have to have a common denominator. So this equals 7 to the 1/2 times a 1/3. Oh, we did in this problem up here. Yeah, that problem right there. And when doing so, we get 7 to the 1/6. And this is an appropriate answer. We can leave it like that. Now, if you were to convert this, it also will look aesthetically pleasing like this. 6 to the 7th power. That is also right. This was very ugly looking, but these two, I accept either one. I like this, but we take either one. But this is what today's assignment is as far as converting. If you have any questions, y'all, feel free to ask, but have a wonderful day.